Hello everyone, I am Professor Anishwara and I welcome you all in our next series of video lecture. In this video lecture, we will be discussing stator core design, specifically for three-phase induction motor. So in case of stator core design, let us see what type of parameters we have to consider. So first, we have to consider stator slot design. In case of stator slot design, we have stator slot geometry. Then we have to select total number of stator slots. Then sizing of the stator slot is very important. Then we have to consider slot insulation. Then stator teeth design. And then at the last, we have to consider depth of the stator core. So in this video lecture, we will discuss all these parameters one by one. So let us start with stator slot geometry. In case of three-phase induction motor, we have basically two options. One option that is open slot and another option that is semi-closed slot. Now, both the slots have certain advantage as well as certain disadvantages. Let us consider for open slot. One of the advantage of open slot is a reduction in excessive slot leakage. Hence, leakage reactance is reduced. When leakage reactance is reduced, we know that the diameter of the circle diagram increase and overload capacity of the machine also increase. But due to increased air gap contraction factor, magnetizing current is quite large and that leads to poor power factor. In case of three-phase induction motor, power factor is very important. So open type of slots are rarely used in design consideration for three-phase induction motor. So second option is a semi-closed slot. Main advantage of semi-closed slot, that is a less air gap contraction factor, hence a reduced magnetizing current and improved power factor. At the same time, tooth pulsation losses are reduced and operation is with very less noise. So operation is with very less noise. So semi-enclosed slots are mostly preferred in design of three-phase induction motor. In the figure, we can see open type as well as semi-closed type of slot. Our next parameter, that is number of stator slots. To define total number of stator slots are very important in case of stator core designing. We have to follow certain factors. We have to consider certain factors while deciding the total number of stator slots. Let us consider one by one. The first is tooth pulsation loss. By using large number of narrow slots, variation in the air gap reluctance can be minimized and hence tooth pulsation loss is very less and operation is without noise. Second parameter, that is a leakage reactance. By using large number of slots, more insulation and so reluctance path for the leakage flux will be more. So leakage reactance will reduce. This will increase the diameter of the circle diagram and overload capacity of the motor eventually increase. We are discussing certain factors. Some of the factors indicates that we should consider for a larger number of slots and some of the factors will indicate that a larger number of slots have certain disadvantage also. So we'll be discussing one by one. We have considered tooth pulsation loss as well as leakage reactance. In both the case, it indicates that a larger number of stator slots are advantage. Our third factor, that is mechanical difficulties. Large number of slots will give smaller slot pitch, and if tooth width is half of the slot pitch, it will result in a weak mechanical structure. It requires certain supports during lamination, and it become obstacle in our ventilation system. At the same time, reduced cross section of the teeth will give large flux density and hence more magnetizing current and higher iron losses. Our next factor, that is cost. Large number of slot obviously need more number of coils to be wound, which will increase the labor cost. And last, that is magnetizing current and coil losses. Using a large number of stator slot in higher flux density in tooth section and eventually higher magnetizing current, poor power factor, and increased iron losses. So this way we have to consider all the factors while deciding the total number of stator slot. Our next design factor, that is a guideline. We have to follow certain guideline while deciding the number of stator slots. First, slots per pole per phase. We should have integral number of slots per pole per phase, and normally we consider 3 to 5 slots per pole per phase while designing or while deciding the stator slots. Sometimes we consider narrow range and we select between 3 to 4 slots per pole per phase. Then we have a slot pitch. We normally take 15 to 25 millimeter for open type of slot or less than 15 millimeter. Sometimes mostly we take a 10 millimeter. So 10 millimeter to 15 millimeter for semi-closed type of slot. Then we have number of conductor per slot. Specifically in case of double layer winding, we have to take even number, and it is always even integer number. So this much of guideline we must consider while deciding the number of stator slots. Then we have slot pitch. Let us derive or let us see how mathematically slot pitch can be given. So slot pitch, that is toe, 1s is for slot and 1s is for stator. So toe SS, that is slot pitch, is equal to gap surface and divided by total number of stator slot. So pi d, that is our circumference, that is gap surface at the air gap, and divided by total number of stator slot, where S, that is number of stator slot, S for stator and S for slot. And we discussed that tau SS, that is stator slot pitch. Then we have to consider slot area. So ASS, 1S is for a slot, 1S is for stator, and small a we have taken to consider area. So slot area, that is equal to copper area per slot divided by space factor. So how to decide copper area per slot? So we have total number of conductor per slot and multiplied by cross section area of the conductor. So it gives us copper area, total copper area per slot, and we have to consider insulation also during designing space required for the insulation. So it is divided by space factor. So space factor normally we take in between 0.25 to 0.4 depending upon the size of the motor and the voltage rating of the machine. Z, SS, that is stator conductor per slot. AS, that is area of conductor. So this way we can decide the slot area. But after deciding or after estimating slot area, our next step, that is to decide the slot dimension. So slot dimension, we normally consider depth of the slot and width of the slot. Now we have to consider how to take depth as well as width. Now for example, two wide slot gives thin tooth. Now we know that if tooth area is very less, then we have increased flux density. There is always a chance of saturation. Else, we have higher magnetizing current, higher iron losses, and poor power factor. So we should not consider too wide slot that result in thin tooth. Normally, we have to consider cross-section area of the tooth in such a way that the mean flux density in the tooth varies 1.3 to 1.7 Weber per millimeter square. Mostly we take 1.7 Weber per millimeter square as the maximum flux density. Then two wide tooth. Now tooth. The cross-section area or width of the tooth is too large. Then it results in narrow and deeper slot. So narrow and deeper slot, in case of narrow and deeper slot, leakage reactance increase. If leakage reactance increase, then we have less diameter of the circle diagram and eventually overload capacity of the machine decrease. So we should not consider too wide slot. At the same time, too wide tooth, that is also not advantage. So as a rule of thumb, we normally take a ratio of slot depth to width in between 3 to 6. Depth to width ratio, we normally consider 3 to 6. So this way, after designing slot area, we can consider the slot dimension. So next step, that is a slot insulation. Depending upon the voltage rating and depending upon whether it is a single layer burst winding or double layer lap or wave winding, we have to consider slot insulation. As shown in the figure, we have lip area, then this is our wedge area. We have conductor or we have coil here. We require different insulation level. It is indicated as a top liner, slot liner. We have coil separators. Coil insulation is also required. So this way we can have to consider slot insulation, and at the same time considering slot insulation, we consider space factor, which will decide again the area of the slot. So this way we have to consider slot insulation. So after considering slot insulation in stator design, we have to further consider design of stator teeth. In case of stator teeth, the minimum width of the teeth is very important because it gives the maximum teeth flux density. So width of the teeth can be decided as per the equation, that is flux divided by flux density and area. So flux density, that is B, and T for teeth. So maximum flux density can be considered as 1.7 Weber per meter square. So to decide width of the teeth for stator, S for stator, and minimum, we have to take maximum flux density, that is 1.7 Weber per meter square, as we discussed. So as shown in the equation, we have flux, maximum flux, and divided by flux density and area. So area, that is depth and width. So we are to select width. So depth we have taken, so that is length of teeth. So teeth flux density, that is we have already discussed, that is B and T for teeth. So BT flux density for teeth. Then flux 5M, that is maximum flux per pole. S and S, that is the number of stator slots. P is number of pole, and Li, that is iron length of the teeth. So this way we are able to consider, or we have to decide teeth, minimum width of the teeth. Our next phase in stator design, that is stator depth of the core. Again, while deciding the depth of the stator core, we have to consider the flux density. 1.3 to 1.5 Weber per meter square, that is maximum flux density we normally choose for core of the stator. As shown in the figure, we have D, that is our main dimension, that is stator bore diameter, and DO, that is the overall outer diameter of the stator frame. So while calculating outer diameter, we have to consider depth of the slot, that is indicated by small d and SS. One S is for stator and one S is for slot. So small d SS, that is the depth of the stator slot. And then we have to consider depth of the stator core. So D CS, C is for core and S is for slot. So depth of the stator core. So eventually, while calculating our overall diameter, we have to consider depth of the slot as well as depth of the core also. So outer diameter of the core, as just we discussed, that it is main diameter D plus 2 times at the upper side as well as at the bottom side. So we have to consider 2 times depth of the stator slot, and we have to add depth of the core. So ultimately outer diameter is D plus 2 times DSS plus 2 DCS. Then how to select stator depth of the core? Just we discussed that depth of the stator core we have to consider based on flux density we offer for the stator core, and just we discussed that in between 1.3 to 1.5 Weber per meter square, that is at the most maximum flux density we can consider for depth of the core. Flux in stator core, that is half of the total flux per pole. This much of flux are passing through the core. So based on this, we can consider area of the stator core. So area is nothing but a flux divided by flux density. So total flux passing through the stator core, that is half of the flux per pole, and divided by flux density of the stator core, B and CS. C is for core and S is for stator. So this way we are able to calculate total area of the slot. Another way of calculating area of the stator core, that is length multiplied by depth. So Li, that is length of the teeth, and depth of the core, stator core. So this way also we can able to calculate the area of the stator core. And if we equate equation number 1 and 2, we have this equation, and from this equation we can easily able to calculate depth of the stator core. So equation is self-indicating in this way. So this depth of the stator core can be decided. So this way we have, in this video lecture, we have considered overall stator core designing. In previous lecture we have discussed stator winding design. So stator core as well as stator winding design we have completed. Keep watching my video, and we'll be discussing more design parameters. So I will stop here. Thank you very much.